Good morning friends. Today we are going to see the basics of magnetism such that we will be able to understand the magnetic materials and their various applications in various electrical and electronic engineering purposes. Okay, now consider a basic bar magnet like this, where there will be one north pole and one magnetic south pole. The length between the magnetic north pole and magnetic south pole, let us call it as L, and area of each face is A. Now every magnetic material has two poles, north pole and south pole, okay, such that it is known as a dipole. It is known as a dipole. Every dipole has a dipole moment. Okay, the dipole moment mu bar of a bar magnet can be defined as strength of each pole into the distance between the two poles. Distance between two poles is L. So the pole strength units are ampere meter and length units are meter into meter, ampere meter square, or joule per Tesla we can write. Joule per Tesla. This is how we define magnetic dipole moment of a bar magnet, right? Pole strength multiplied by analogy with an electric dipole, right? Strength of each pole, that is charge on either pole, multiplied with the distance between the two poles. Here, strength of each pole and multiplied by the distance between them is defined as dipole moment. Units are ampere meter square or joule per Tesla. Okay, right? And its direction is always from south pole to north pole. It's a vector quantity. Magnitude of magnetic dipole moment is pole strength multiplied by distance between the two poles. Units are ampere meter square or joule per Tesla, right? Direction is always from south pole to north pole. Remember that point. Okay, direction of dipole moment is always from south pole to north pole. Now we will define what is known as intensity of magnetization or simply magnetization. Okay, it is mostly denoted as M, or, right, equally popular notation is I also. Means you can use the intensity of magnetization or simply magnetization can be denoted by either M or I. Both are equally popular. Okay, this is nothing but defined as magnetic dipole moment. Magnetic dipole moment per unit volume of the magnet. This is how we define dipole moment. Now I will define one more parameter called intensity of magnetization. Intensity of magnetization or simply magnetization. It is denoted by M bar or I bar. Both are equally popular notations. Anything you may find in the exam, right? How do we define what is intensity of magnetization? It is the magnetic dipole moment per unit volume of the bar magnet. That is magnetic dipole moment, as we have seen earlier, it is nothing but mu bar by volume of the material. This will become our M bar. M bar equal to magnetic dipole moment per unit volume. So what is volume of this bar magnet? Area of each face multiplied by the length between the two poles, that is nothing but area into length will give you the volume. Okay, units of dipole moment are ampere meter square by volume by meter cube, nothing but ampere per meter we get here. Now what is mu bar? Mu bar formula is, right, pole strength multiplied by distance by volume is nothing but area into distance L. So L and L get cancelled here. Okay, we are getting M by A. This is ampere meter by area, ampere per meter. Okay, so units of magnetization or intensity of magnetization are ampere per meter, right? We can define it in two ways. One is dipole moment per unit volume, or we can define it as magnetic pole strength per unit face area of the magnet. Either way you can define intensity of magnetization. Whatever it is, intensity of magnetization or simply magnetization denoted by either M or I is dipole moment per unit volume or pole strength per unit face area. This is one parameter in magnetism which is important. Now in magnetism we usually have three vectors. Okay, one is intensity of magnetization, or simply magnetization we have already seen. Okay, units are ampere per meter. And next one is what is known as B bar. B bar is called magnetic field strength or magnetic field induction, or number of what? How do we define B bar? B bar is number of lines of force per unit area. Okay, number of magnetic lines of force passing through unit area is called magnetic flux density or magnetic field strength or magnetic induction. Either way you can call it. B bar units are Weber per meter square or Tesla. Okay, Weber per meter square or Tesla. Tesla is a very big unit of magnetism. Okay, 1 Tesla equal to 10 to the power 4 Gauss. 1 Tesla equal to 10 to the power 4. 10,000 Gauss is 1 Tesla. Okay, very big unit of magnetic field strength. So this is one unit of one important vector in magnetostatics or magnetism, B bar. What is B bar? It is magnetic flux density or magnetic field induction or magnetic field strength we can call. Units are Weber per meter square or Tesla. Since Tesla is a very big unit of magnetism, right? 1 Tesla is equal to 10 to the power 4 Gauss or 10,000 Gauss. Now we will define another parameter called H. Okay, H is called magnetic field intensity. Okay, its units are ampere per meter. Okay, here they are Weber per meter square for B. Okay, and we have already seen intensity of magnetization or magnetization M bar equal to, right, dipole moment per unit volume. Its units are also ampere per meter. Okay, so B is magnetic field strength, H is magnetic field intensity, M is intensity of magnetization or simply magnetization. Okay, now you take vacuum or free space. Okay, in free space I'll apply some magnetic field of intensity H. I'll apply some magnetic field of intensity H like this. H is magnetic field intensity. Okay, H bar is a vector. Units are ampere per meter. Now in vacuum, how many lines of force are passing through unit area? How many lines of force are passing through unit area? That is known as B. Okay, B is magnetic field strength. It is number of lines of force passing through unit area. Okay, in vacuum, if I apply some magnetic field of intensity H, the number of lines of force passing through unit area, I'll call it as B naught. Now, just guess how many lines of force will pass through a unit area in vacuum when you apply some H. Depends on what factors? Depends on H only. Okay, more powerful magnetic field intensity apply, more will be the number of lines of force. So B naught is proportional to H, or B naught equal to mu naught HI rate. Mu naught is called permeability of free space. Okay, its value is 4 pi into 10 to the power minus 7 Henry per meter. 4 pi into 10 to the power minus 7 Henry per meter. B naught is number of magnetic lines of force passing through unit area in vacuum. Okay, now okay, in vacuum per unit area, B naught number of lines of force are passing. What happens when I put some medium here? That medium is let me say my hand only. Okay, through my hand, per unit area of my hand, how many lines of force are passing through? I'll call it as B. Okay, now how many lines of force will pass through unit area through my hand? Also depends on H only. More powerful H I apply, more number of lines of force will pass through. Less force, less field you apply, less number of lines of force will pass through. So B is also proportional to H, okay, or B equal to mu H I will write. B equal to mu H I will write. Now mu is called absolute permeability of the medium. Okay, absolute permeability of the medium. absolute permeability of that particular medium, whichever medium we are opting for. Okay, now why B inside my hand is different? My hand is medium other than vacuum. In vacuum, some number of lines of force are passing through unit area, but when I put some medium there, I'll put this pen, or I'll put my hand, or I'll put some wooden piece or something like that. If any other medium is put, the number of lines of force are found to be different. That number of lines of force per unit area is also proportional to H only, but since B and B naught are different, I'll call B is equal to mu H. I'll write mu is called absolute permeability of the medium. Okay, now the ratio B by B naught, that is the magnetic field strength in vacuum by magnetic field strength in a medium, the ratio B by B naught equal to, right, mu H by mu naught equal to mu by mu naught is equal to mu R is called relative permeability. Okay, it is a dimensionless quantity, ratio of similar things. Okay, so the ratio B by B naught, what is B? Magnetic field, intense magnetic field strength inside a medium. B naught is magnetic field strength in vacuum, is equal to mu by mu naught equal to mu R. Mu R is nothing but relative permeability. Okay, it's dimensionless, it has no units. Okay, now why B is different from B naught? Inside the medium, why the number of lines of force are different? Means something must be happening inside the medium such that the number of lines of force are different from those in vacuum. Okay, number of lines of force in vacuum is B naught, number of lines of force in any medium is B. Why B and B naught are different? Means something is happening inside the medium such that B is different from B naught. Sometimes B can be more than B naught, sometimes B can be less than B naught also, depending on the property of the medium. Okay, now now we have seen the three magnetic field vectors B, right? Next one is intensity, magnetic field intensity H, and intensity of magnetization M bar or I bar. B bar, M bar and H bar are the three magnetic field vectors. They are related to each other as B bar equal to mu naught into M bar plus H bar. B bar equal to mu naught into M bar plus H bar. How this relation has come, we will see in later classes. Okay, now just now we have seen B equal to mu H, so I will put mu H here is equal to mu naught into, right, M bar plus H bar. Okay, mu H equal to mu naught into M bar plus H bar. Now slightly rearrange the terms here, slightly rearrange the terms. Okay, right, take that mu naught to this side and bring that mu naught to this side and take this H to the other side. So mu by mu naught equal to, this H goes to the other side, it is M bar by H bar plus 1. Okay, now what is mu by mu naught? Just now we have seen mu by mu naught is nothing but relative permeability. It is mu R. So mu R equal to, the ratio M bar by H bar is defined as magnetic susceptibility chi. Magnetic susceptibility chi plus 1. This is an important relation, right, in magnetism. Relative permeability mu R equal to chi plus 1, where chi is called magnetic susceptibility. Okay, magnetic susceptibility. Chi is nothing but M bar by, chi is M bar by H bar is defined as chi. Okay, so mu R equal to chi plus 1. Right, what is chi? What is the meaning of susceptibility? Okay, now try to understand. Somebody susceptible to something means what? He is prone to, or he is affected by in a efficient or in an effective manner. If he gets affected, okay, he is susceptible to something, means he is prone to that something. Okay, susceptibility means the effect of an external magnetic field on a medium is a measure of its susceptibility. How effectively one material gets affected by an external magnetic field is measured by something known as susceptibility. Permeability means what? How freely the magnetic lines of force will be able to permeate through the medium, penetrate through the medium, that is known as permeability. A material has more permeability, this material has less permeability, means more number of lines of force can pass through this material, less number of lines of force can pass through this material. This material is more susceptible, means it gets affected by the external magnetic field, right? This gets less affected by the external magnetic field. This one susceptibility is less, that one susceptibility is more. Okay, right? Susceptibility. Now, depending on the relative values of mu r and chi, we can classify all magnetic materials. Okay. Now, we know that B by B naught equal to mu by mu naught equal to mu r, relative permeability, right? Relative permeability mu r equal to chi plus 1, where chi is called susceptibility m bar by h bar. What is m bar? Magnetic dipole moment induced per unit volume inside the material by the magnetic field intensity is known as susceptibility. This is also dimensionless parameter. This is also dimensionless parameter. Okay. Now, they have no units. Now, depending on the relative values of mu r and chi, we can classify magnetic materials into different types. Okay, now what do? I will take some material like this. Okay, let us name it as P. I am applying some H in one direction like this. Because of the action of this H, suppose say a small magnetic dipole moment per unit volume m bar gets created inside the material in opposite direction to H bar, say. Okay, m bar and h bar in opposite direction, right? And m bar is very small. What is m bar? Dipole moment induced per unit volume inside, per unit volume of the material. Now, then what happens to chi? Chi equal to m bar by h bar. Okay, right? M is in opposite direction to h. So, two vectors are in opposite direction. We denote it by negative sign. Means susceptibility for such materials is negative, and since m bar is very small, okay, chi is also very small. Chi is also very small. So, for some materials, chi is negative and very small. Okay, when chi is negative and very small, how small it will be? Chi equal to, right, minus 0.00001 of that order. Extremely small value. Okay, such that mu r becomes what? Such that mu r equal to chi plus 1 minus 0.0001, that is nothing but 0.9999 something like that we get. Okay, mu r is less than 1 slightly, less than 1 slightly. Okay, mu r is less than 1 slightly. Now, mu r is less than 1 slightly means B is also less than B naught slightly. Okay, right? B is less than B naught slightly. Such materials are called diamagnetic materials. Such materials are called diamagnetic materials. Okay, so what are the properties of diamagnetic materials? Susceptibility chi is negative and very small. How small they are? Minus 0.00001 something like that. That is minus 1 into of the order of 10 to the power minus 5. Okay, such that relative permeability mu r equal to 0.9999 something like that. Okay, that is less than 1 slightly, such that B is also less than B naught slightly. Such materials are called diamagnetic materials. Okay, right? Now, we will go to the other one. Okay, I'll take some other material. Okay, I'll apply same H value in the same direction. I'll call this as Q, material Q. Now, inside this material, say small magnetization M bar gets induced in the direction of H bar. If you remember, in diamagnetic material, small magnetization got induced in opposite direction to H bar. Small magnetization got induced in opposite direction to H bar, whereas here, right, they are getting induced in the direction of H bar only. In the direction of H bar only, such that relative susceptibility chi equal to M bar by H bar. M and H both are in the same direction, such that susceptibility will be positive here. But since M is very small, okay, I'll write, right, chi is also very small. Chi is also very small. Okay, how small chi will be? Chi equal to, right, 0.00001, something like that. Okay, extremely small. Then chi is, right, positive and very small, right? Chi is nothing but mu r equal to chi plus 1. Chi is very small, 0.000, something like that, such that mu r will be 1.00001, something like that. That is mu r greater than 1 slightly. Mu r greater than 1 slightly. When mu r is greater than 1 slightly, right, the ratio b by b naught equal to mu r, right, b also will be greater than b naught slightly. Okay, ratio will be b is greater than b naught slightly. Such materials are called paramagnetic materials. Such materials are called paramagnetic materials. So what are the properties of paramagnetic materials? Susceptibility chi is positive and very small. Okay, how much will be chi? Chi equal to 0.501, that is of the order of 10 to the power minus 5. Only thing is chi is positive here, 10 to the power minus 5. Chi will be negative in diamagnetic materials, minus 10 to the power minus 5. Mu r is greater than 1 slightly, b is greater than b naught slightly. Okay, such materials are called paramagnetic materials. Next one, we'll see another type of material called ferromagnetic materials. Now I'll take another material. Let me call it as R. I am applying same H in the same direction. Now in this material, say large magnetization, that is large dipole moment m bar gets induced in the direction of h bar only, such that susceptibility chi becomes what? Chi equal to m bar by h bar. Okay, m and h bar are in the same direction, such that chi is said to be positive. Since m is very large, okay, the ratio m bar by h bar also will be very large, or chi will be very large. Chi will be very large here. How large? We cannot tell. It can be 500, it can be 1000, it can be 10,000. Okay, right? It can take any value, right? So chi is positive and very large, such that mu r is chi plus 1, chi is 10,000, right, 20,000, like that, such that mu r will be greater than 1, very much greater than 1. When mu r is very much greater than 1, right, b will be very much greater than b naught. B will be very much greater than B naught. Such materials are known as ferromagnetic materials. So what are the properties of ferromagnetic materials now? Chi is positive and very large. Very large means it can be hundreds, it can be thousands, tens of thousands also. Mu r also will be very much greater than 1. Nowadays people are making materials which are having mu r values, right, 80,000, 1 lakh, more than 1 lakh also. So B will be very much greater than B naught. Means inside the material the magnetic lines of force will be, right, thousands of times more than the magnetic lines of force in vacuum. Now let us sum them up. Okay, we have diamagnetic materials here, chi negative and very small. Okay, paramagnetic materials there and ferromagnetic materials there. What are the examples of diamagnetic materials? Diamagnetic materials, the examples are, I'll give you some examples which we use materials in our everyday life, which materials we use in our everyday life. What are the important thing is water. Okay, important thing is water. Okay, next one, copper, silver, gold. Copper, silver, gold, they are also diamagnetic materials. Diamond is also diamagnetic material. Okay, diamond, quartz also is a diamagnetic material. Okay, glass is also diamagnetic material. Okay, glass is diamagnetic material, right? These are some materials, silicon, germanium, which are important for electronic students. Okay, right? So what are the examples of diamagnetic materials? Diamagnetic materials, water, copper, silver, gold, all these three are noble metals. All these three are noble metals. Okay, diamond is there, quartz is there, right, glass, etc. Now what is the order of susceptibility? Susceptibility will be -1 into 10 to the power -5, extremely small value. Okay, mu r will be, 0.9999, something like that. And these are the materials which are examples of diamagnetic materials, right, which we find in nature. And one material, important one, is bismuth. Okay, bismuth is the best diamagnetic material available in nature. Okay, natural diamagnetic material. Bismuth susceptibility is minus 0.00017. That is 17 into minus 17 into 10 to the power minus 5. This is the most powerful diamagnetic material available naturally. Okay, now let us come to paramagnetic materials. Okay, paramagnetic materials, chi is positive and very small. How much it is? 0.00001, etc. That is, it will be the order of 1 into 10 to the power minus 5. The only difference between para and dia is that this one is minus 1 into 10 to the power minus 5. This one is plus 1 into 10 to the power minus 5. Right? Mu r is greater than 1 slightly. What are the examples? What are the examples for paramagnetic materials? First, water is essential for us. Next one is air. Air is paramagnetic material. Okay, right? And what does air contain? 78-79% of air is nothing but nitrogen. So nitrogen must also be paramagnetic material. Nitrogen gas is paramagnetic material. Next, remaining around 20% is of air is oxygen. So oxygen must also be paramagnetic material. So what are the examples of paramagnetic materials? Air, right? Nitrogen, oxygen gas, and liquid oxygen also. I can write liquid oxygen. Liquid oxygen is also paramagnetic material. Okay, platinum is one paramagnetic material. Okay, platinum is one paramagnetic material. Cobalt oxide, nickel sulfate, like that we have many paramagnetic materials as we can give as examples. Okay, next one, ferromagnetic materials. What are the properties of ferromagnetic materials? Chi is positive and very large. Chi is positive and very large. Mu r is greater than 1, right? B is very much greater than B naught. Mu r is also very much greater than 1. What are the examples of ferromagnetic materials? Natural ferromagnetic materials are very less in number. Okay, they are nothing but iron, okay, cobalt, nickel, gadolinium, and dysprosium. These are the 5 elements which are ferromagnetic materials. Okay, right? So what are the examples of ferro? We can quote only 5: iron, cobalt, nickel, gadolinium, and dysprosium. We don't use much of gadolinium or dysprosium because of their drawbacks. Okay, mostly ferromagnetic materials, most of the people quote only iron, cobalt, and nickel. Okay, these are the prominent ferromagnetic materials, right? Now, which materials are useful industrially? Okay, as we have seen, the material should be magnetic, means its permeability and susceptibility should be very large. We have seen in the case of both dia and para, susceptibility is very small. Okay, negative or positive doesn't matter. Okay, susceptibility is very small. Mu r values are also very small, so they don't have much engineering applications. Paramagnetic materials and diamagnetic materials do not have much engineering applications. An electrical engineer or a mechanical engineer calls something as a magnet means it must be ferromagnetic material only. It must be ferromagnetic material only. Okay, because ferromagnetic materials only are useful, right? Now, I've told you about 2 more different types of magnetic materials. One is antiferro. Okay, antiferromagnetism and ferrimagnetism. These are all special cases of ferromagnetic materials. Okay, these are nothing but special cases of ferromagnetic materials. What are antiferro and what are ferrimagnetic materials? Okay, how they are different from ferromagnetic materials? Okay, what are the uses of these ferro and ferrimagnetic materials will be seen in the next lecture. Thank you.